In this video, we'll talk about what recurrence relations are. So a recurrence relation defines the nth term of a sequence in terms of some of the previous terms. So let's give an example. I'm going to let f of 0 be 0, f of 1 be 1, and for n greater than or equal to 2, f of n equals fn minus 1 plus fn minus 2. So that means fn will be equal to, these are the two previous terms added together. And I want to write the first 6 terms of the sequence. So first, a bit of notation. If I write fn within curly brackets like this, that's just the notation that indicates the sequence. So the first term is when n equals 0, but I have that already. I know that that term is 0. I have f1 as well, that's given to be 1. And once n is greater than or equal to 2, as it is here, now I start to use this formula, which says, well, add the two previous terms. If I plug in 2 in for the n, the other side becomes f1 plus f0. Well, that's 1 plus 0, which is 1. If I add the two previous terms together, I get 1. If I plug 3 in for the n in this formula, I get f2 plus f1, which is 1 plus 1, and that's 2. Okay, for the next two terms, let's do it a bit more quickly. If I add the two previous terms, 2 and 1, I get 3. And then if I add the 2 and the 3 together, I get 5. If I keep going like this, 3 plus 5 is 8, and then 5 plus 8 is 13, 8 plus 13 is 21, and we get the famous Fibonacci sequence. So this fun fact, it actually dates back 1400 years before Fibonacci to Pingala in India. All right, so let's do an example. I want to prove that the sequence an, and this notation means I first start off by plugging 0 in. That's the first value I plug in for n. And the infinity means, well, there are infinitely many terms in the sequence. So I want to prove that the formula an equals a negative 2 to the n power is a solution of this recurrence relation. Okay, so what does that mean? So if I write out some of the terms of the sequence, so I'm starting at n equals 0, negative 2 to the 0 is just 1. Negative 2 to the 1 is negative 2. Negative 2 to the 2 is 4. To the third power would be negative 8, and so on. So those are the terms of this sequence. And what I'm first going to do is give an insufficient proof of why this is a solution to that formula. So let's test this out for a couple of the values here. And the problem says the sequence starts when n equals 0, which means this first term is a0, then it's a1, then it's a2. So a2 is 4, and then a3 is negative 8, and so on. So let's test this out, recurrence out, for a couple of values of n. For example, if I plug n equals 2 into that, I'll get a subscript 2 equals question mark a1 plus 6a0. So I want to know if this is true. And if I plug in my values for these things, I get 4 equals negative 2 plus 6 times 1, question mark. But the right-hand side just equals 4. So I get 4 equals 4. Check. That's looking good. Okay, so maybe let's test the next value. Let's plug in 3. I'll plug in 3 into my recurrence. Okay, and I'll get a3 equals question mark a2 plus 6a1. And if I plug in the terms we got from this formula, a3 is negative 8. Does that equal question mark? Does it equal 4 plus 6 times negative 2? Oh, this just becomes negative 8 equals negative 8. So check mark, that works as well. But unfortunately, this only shows that it's worked for 2 and 3. I could keep going like this and try 4 and 5 and 6 and so on, but there's infinitely many terms in that sequence. So if I go about it like this, it's going to take me forever to check all of these. So I want a more succinct way of doing this. So let's talk about how we actually prove this. What I'm going to do is I'm going to let an be the formula that's given, negative 2 to the n, And to show that that's the solution to this recurrence relation, I need to be able to plug it in to this equation and show that both sides end up equaling each other. So then what I'm going to do is I'm going to plug into the right side first. So if I do that, my an minus 1 plus 6an minus 2 ends up equaling, and if I plug in n minus 1 for the n, we get negative 2 to the n minus 1 power. Then I got plus 6 times, if I plug n minus 2 in, we'll get times negative 2 to the n minus 2. Okay, so let's simplify this. I can factor out negative 2 to the n minus 2, because that's the smaller of the exponents. When I do that, from the first term, we'll be left with negative 2. And then from the next term, plus 6. All right, so the thing in the parentheses will just become 4. So what I have is negative 2 to the n minus 2, and I'm going to rewrite the 4 as negative 2 squared. And the reason that I'm doing that is if I make the bases the same, now I can use exponent properties. Because this equals negative 2 to the, and I add the powers together, which gives me n. But negative 2 to the n, well, that was an. So we just got that this equals the original thing on the left-hand side. So we've just shown that the right-hand side equals the left-hand side, provided that we are plugging in this formula that the problem told me to plug in. But that's precisely what it takes to show that it's a solution. Okay, so this completes the proof, because this shows that this formula does indeed work. It makes the two sides equal each other. So the next video, we will talk a little bit about, well, how do I go in the other direction? Like how, if I'm given a recurrence like this, can I derive the formula? Because that's a more challenging problem.